In last video we made a linear regression model. Linear regression. Okay. We used scikit-learn for it. And what we did, let me recap it for you. We initialized a model with this linear regression, and then what we did, model dot fit, and we passed x and y to it. All right. What was this y? It was our output. And what was x? X was the input feature. But what we don't know is what happens inside this fit function, because we didn't implement any of this. So we need to know, right, what happens inside this linear regression model. So actually, see, what we know is linear regression finds the best fit line for us, which is y hat equal to mx plus c, and let's say this is y and this is x. Okay, this c is the intercept. Okay, so this is our c, and this m is slope. So at any point, if I draw this theta, then slope will be tan of theta. So this is my intercept. All right. So this is simple equation of a line. But what happens in linear regression? Like, what is this? How is this even relevant to me? How am I going to train my model based on this? So again, let's take another example. Like this is our graph, and our input features are like this, distributed all over. Let's say this and this. Okay. So what my model did, it it randomly picks a line like this, and let's say this line again is y equal to mx plus, okay, wait, this is a, this is again y equal to mx plus c. All right, but see, this is a randomly initialized line. What I will do, I will check what is the distance of these points from my best fit line. Okay, now see, I can see that this distance can be minimized. So I can actually make a better line than this. So based on this, I will try to minimize this distance, okay? This distance between points. So I'll come up with another line, okay? I'll say, okay, let's now try this line, okay? And again, this is something like y is equal to mx plus c, but this time m would be something different, c would be something different, but this line is actually a better line than that one, because see, the distance between points from this line is actually lesser than the other one. Okay, so this is what happens in the linear regression model. We try to minimize this error. So to calculate this distance between point, we use something called as a cost function. uh, Basically it will be the mean of squared error. So what I'll do, let's say I have n training examples, n examples. See, these are like 1 2 3 up to n. Okay, these n examples, what I'll do, I'll make a cost function based on these examples, that will be 1 upon 2 of n, where n are my training examples. Then I'll just start from I equal to 1 and sum up to whole n, all of these training example. And what I'll do, I'll just do this, okay, square of the error. See, suppose the value here would be y and predicted value is y hat. I'll just square their distance and sum it up. And what I have to do in linear regression, I have to actually just minimize this. Okay, I have to minimize this thing. So when I will minimize this, whichever line minimizes this for me, that is going to be my what, best fit line. Got it? So till now it must be clear for you, but then How am I going to minimize it? So what I'll do, let's say this cost function is called j of m and c, okay, because line was y equal to mx plus c, and now y is dependent on m and c. See, m and c are constants, so I can actually alter the values of these, okay. So let's say this is j of m and c, and this side I'll have m, this side I'll have c, okay, and again j of m and c, and then I'll see for different values of m, I'm getting a curve like this, okay, and similarly for different values of c, I'm getting a curve like this. So this is the global optima for me, okay, and whichever value is going to give me global optima, that values of m and c I'm going to keep. All right, so let's see. The algorithm for this would be something like repeat until it converges. What I mean by that, global minima. Okay, what I'll do, I'll update my m to be m minus, what I'll subtract, summation of I equal to 0 to n. What is n? N is my training examples, number of examples I have in that set, and then I'll have this y hat minus y whole square. All right, and then again this is another constant 2n. I'll do this. Okay, then similarly for c, I'll update c as c minus this same thing. Okay, 1 upon 2n, and summation up to I equal to 0 to n, then y hat minus y whole square. All right, now see, I do not want that this to go very steady. To control speed of this convergence, I am going to use another hyperparameter, which is alpha, and this alpha is nothing other than our learning rate, and let's say this is 0.001. Okay, see, value of alpha should be neither too low nor too high. So this is another hyperparameter that you train. See, if you have very small value of alpha, this going down to the slope is going to be really slow, and it will take very long time. On the other hand, if you have very large value of alpha, it will just shoot to different directions and is not going to reach global optima unless and until you have great luck in doing so. So we take very optimal and adjusted value of learning rate. And what is this? This algorithm is nothing else than the gradient descent. Okay, this is the actual gradient descent algorithm. People make so much hype about it, but it's very simple. Now, other thing that I will like to tell you that it is not always a case for linear regression to be like y equal to mx plus c. Okay, there may be cases where you have multiple features. Okay, where y is going to be dependent upon multiple features like m1 x1 plus m2 x2 plus m3 x3 plus m4 x4 plus c. Okay, in such cases this y hat is going to be dependent on upon multiple features, so our plane for four-dimensional stuffs would look something like this. Okay, these are four planes, and in such cases this graph is going to be multidimensional, and this gradient descent will try to minimize it to a global minima with respect to all of these, and these updations would be simultaneous, and that's how our linear regression model works. So it's not that big of deal, but people make so much hype about the mathematical intuition behind this. This is nothing but this is the derivative. Okay, so what is actually happening? We are just, you know, we are just going down to the slope, making derivatives subtract from each other. All right. So this is it. Because this part, okay, let me change the color. This seems fine. Okay, so this part is nothing else than what I'll say, alpha of differential of J, M, and C with respect to differential of, alright. So this is just a partial derivative, what I did here. So see, mathematical intuition behind these things is not really up to the hype that we make about it. So this is very simple. I hope you understand it, and like, share, and subscribe if you like the videos.